Hello everyone, and welcome back to Reverse Engineering Linux 32-bit Applications. In this video, we're going to continue our discussion of stack buffer overflows. Now in particular, in a previous video, we had talked about how you could determine the offset to that return address, the one that you want to overwrite. We showed you how you could do that. And in this video, I want to talk about injecting shellcode. So you might say, well, where should I inject this shellcode? A very logical choice would, of course, be to inject it right after that new return address. So let's go ahead and have a look at our simple Python script. And here, as a reminder, we ran our debugger. With our application, we gave it 30 A's. That was just a spacer using the offset we calculated last time. And then we gave it the address of dead beef. Now, here's what we're going to do to modify this is instead of just redirecting it to dead beef, what are we going to do? We are going to find some shellcode, and we're going to shove that in here. So here's what I'm going to do. I'm going to go to shell storm, shellcode. And it would help if I had shellstorm.org. All right, so that's a little bit better. And now I'm going to look for some shellcode. And they have shellcode for all kinds of operating systems, including Linux. So they have ARM-based Linux. That's not what I'm running. And they have Intel 32 and 64-bit Linux. So we will go ahead and find an appropriate shell. So, what kind of shell code do we want to add? This is one of those interesting situations where we have a 32-bit Linux application, but that doesn't mean that it's running on 32-bit Linux. It could be running on 64-bit Linux, which is the case for me. So let's grab some shell code, maybe something like this, and have a look. What is this going to do? This is going to perform a system call. Again, a system call is essentially like a Win32 API call in the Windows world, except it's how we call kernel functions in Linux. Now, if you look at the comments on this particular shell code, you'll notice they use something called syscall. That is a 64-bit assembly call. And here we have the string that's equivalent to this bit of shellcode. So we could try the simplest thing. We could grab this. I can copy it. And I can go back here and I can say, all right, my shellcode equals this. And I'll make it look somewhat prettier. And now I will say param plus equals shellcode. All right, now, one other thing I need to do. I need to fix this address. So in a previous video, we determined that this address should be FFC4 E6 5C. So we have to write that in reverse order. So that would be 5C E6 C4 FF. So let me save that. And let me go ahead and attempt to run this with my script. And I have a little problem because of how I did this on multiple lines. And I will fix that using parentheses. As my line continuation character. I could actually explicitly add a line continuation, but this is a little bit simpler. Okay, so now what? Let me go ahead and run this. Analyze it. Set a breakpoint right here before my stir copy. Hit F2. I will run to that breakpoint. I will step. I will call my stir copy function. And now when I call return, let's see what happens. It has a small problem. So something wasn't exactly right. Let me re-examine my script. And I might immediately notice what the problem was. So let me go ahead and do this. I will just step it through, and then I will show you what is wrong with this. We are slightly off with our address. So what is going on? So once again, I will run to my first breakpoint. I will do my analysis. And now I will back it up to here. Set another breakpoint. Run to that breakpoint. I'm going to call stir copy. You'll notice I have a bunch of A's. This is followed by an address. And then what do I have? I have my shellcode. If I scroll down here a little bit more. So here's the problem. Let me call leave. And now I have this address. And the address is not quite right. So I am just a little bit off. with my address. So what's going to happen is I'm going to try to call my return, and it will be off just a little bit. So let me go back to my script for a second, and I'll make this a little smaller so I can look at both of these at the same time. And let me have a look at this. So you'll notice that I have 6A4258. 6A4258. That was this shellcode that I've added. So I have 30 A's, then I have my shellcode. Now, I want to jump to the shellcode. So the first thing I'll notice is that I am just slightly off. I seem to be off by 1 byte here, and something else has happened. So now I have my shellcode starting here. Now I really wanted to go to a different location. I didn't want to go here to EC or 5C even, but I wanted to go right here, right where this starts. So my address was slightly off. You might say, well, how did that happen? Well, things shifted just a little bit when I changed my script. So let me go ahead and update this and say, all right, I would like to go to FFEA 60F0, but it's actually not quite right. I want to go to EF as my starting point. Now if I go back here a little bit, you'll notice that I have all my 41s, and this should in fact be the correct address. So let me go ahead and change that. And I will change this to an address of this. F0. Six zero. EA. And let's try to run this script another time and see what happens. And it gave me an error. It said end of file and back quote substitution. All right, so what's happening here? Here's what's happening. I am passing in things to my script that are getting interpreted by the shell. So let me fix that. So if I go back here, I can say, all right, let me add in those single ticks again. I'll give it a single tick here, and let me give it a single tick here. Now, normally when we're abusing programs that are accepting things over the network. So having things interpreted by the shell isn't a problem like this. So this is just kind of a complication onto this particular example that we're doing here. Now later, we will show you some network applications, and you'll see that it's not quite as complicated in those conditions. Analyze this part. I will run to my checkpoint. And I will once again set another breakpoint here, and I will run to that. So I'm going to call my overflow, stir copy, and I see I have a bunch of A's. I move my return value of 1. I'll call leave. And now what? So now I have on my stack these values. So what's going on here? Well, there are a couple of things going on. It seems like whenever I change my script, it changes this return value. So now it's FFFDA5AC. So this is a problem because I keep changing this value. Now notice this is my return address, the one that I had, and then I have my shellcode. So again, remind us of what the shellcode looks like. Starts with 6A42, and here it is, 6A4258FE. So all of that's in place, and all of that is correct. So you might say, well, how could I possibly get this to work? Well, it's very fickle, as you can see, as to what this address is going to be. You can have problems because it's going to look at different locations. You might say, well, let me just try this one more time. Let me just try it with FFFDA5B0. And that should point right here, if we're lucky. So let me shut this down again, rerun my script, run to my breakpoint, analyze it, add a second breakpoint, run to that. Step through this section. Once again, I'll call leave. Now when I call leave, I'll notice that this is pointing at FFFDA5B0. So that's not exactly where I need it to be. So you're wondering, well, what's the story here? My stack is kind of a moving target. That's what the story is. So how can I fix this? I can try to find a location in memory that has a call called jump ESP. So what does that do? Jump ESP is a command that says, please jump to the current location of the stack. So run something off of the stack. Now, if I can find that program somewhere, then maybe I'll be in luck. So if I look at the different memory regions, I'll see, all right, which one of these are executable? I see here is an executable one, and also here in libc. So there are a couple of places that I might be able to find a library that'll do what I want. So now what I want to do is I want to search through and find this command. So what's the command that I'm looking for? I am looking for a jump ESP. So the jump ESP command is FFE4. So this is going to be an FFE4. That's what I'm looking for, FFE4. And let me see if I can find it. So there are a couple of places that I've in fact found this here in my code. Now the first place I found it was at F758-7A-A9. So let me go ahead and just use that address. So I'm going to point to F758-7A-A9. And let me try to use that in my script. So I'll go ahead and close this. And now I'm going to change my script. And I'm going to put this in little endin format. So A9, actually doing that backwards. So A9 comes first. And then 7A. And then 5.8. And then finally F7. So this will jump to the current location of the stack. So what we've noticed so far is that in Linux, you can't easily predict the location of the stack. It's kind of randomized. And why is it randomized? Well, it's randomized for a good reason. So that you can't easily do these exploits, just like we have the stack protector turned on by default as well. Windows, the world is a little bit simpler because you don't have a randomized location. However, when you're doing 32-bit Windows, the leading bytes for your stack location are normally zeros. And that's kind of a problem because that's interpreted as a null when you call strcpy, and it does not copy the rest of your string. So, each of the operating systems has its own little idiosyncrasies and problems that you're going to run into. Okay, so let's go ahead and give this a shot. And let's see how this one goes for us. So I'm going to run it. Once again, I will run to my first breakpoint. I will do my analysis. I will set another breakpoint here, and I will run to that. Call my strcpy, call leave, and let's see what happens. So here's my address. We said F758-7A-A9. That's where I'm going to jump to. Sure enough, here is my code. So I will jump there. So I will step in, and it was unhappy with me. So let me run this one more time and see if I can make it somewhat happier. Say, please view the memory regions. And this case, I'm going to go back to libc, and I'm going to once again search through libc for my value, FFE4. And I see it was supposedly found at F75CBAAA9. So it was not found in the exact same location. So once again, you might say, well, what's going on? Well, guess what? In the world of Linux, it does not load things in the exact same location every time. And why not? Well, more protection against these kinds of attacks. So you might be getting the idea that exploiting these buffer overflows in Linux is kind of difficult. And you would be correct, because it is in fact a little bit more difficult. So what could I do to make this better? Let's have a look here at this region. This is our actual program. And is our program loaded in the same location every time or not? That's a good question you can ask yourself. Let me look at my binary searcher and let me see if I can find in this region this value. Now I only have to find the value. I don't need to actually have found a location where this was being used. So it's sufficient just to find this value. And according to what I'm seeing here, it is not finding that value. Again, I will look at my different memory regions. Here's my program. And I need a region that has execute permissions, because if it doesn't have execute permissions, I'm out of luck. So we'll notice that this was loaded at F756C9000. And let's just rerun our program and see if this is in fact loaded at a different location next time. And sure enough, it was. But notice that the program itself was consistently loaded at 08048000. So here we'll notice that our actual program is loaded at the same place in memory, but these libraries are not. So that's a bit of an issue for us. If we're trying to use those locations, these library function locations, in order to jump to a certain place. So you might be thinking, wow, this is kind of difficult. And it is. So we found that we can't just jump to a certain location on the stack, because the stack location keeps changing. And we can't easily jump to a certain location on, right, or rather in a library function, because the loading position of those also changes constantly every time we run our program. So now what? What can we do? Well, here is where things get a little bit interesting, because now you want to try and find an exact location where you can jump to. Now we'll cover that in a future video, how you can get around some of these protections that are sort of built into the compiler and also into the operating system in Linux. But that is all that I wanted to cover in this video. As a reminder, this is but one in a series of videos on reverse engineering, and that is inside of a family of videos and all things InfoSec that are available here at Pentester Academy. So I will look forward to seeing you in this course and some other courses soon. We'll see you then.